It has been over 50 years since we last set foot on the moon. But now, for the first time in a generation, humans are going back. And let me tell you, this is not about planting another flag. This is the start of a whole new chapter in space exploration. We're about to break down the scientific blueprint for Artemis III, a mission that's designed not just to visit the moon, but to stay. You see, the Apollo missions were all about pure exploration, right? Getting there, grabbing some rocks, and coming home. Artemis is fundamentally different. It's really about settlement. The big driving force this time is the hunt for a resource we now know is there: water ice, hiding out in the moon's permanently shadowed polar craters. Finding that water and learning how to use it is the absolute key to building a sustainable human presence beyond Earth.
And that's the crucial thing to understand here. The Artemis program isn't just a series of one-off missions. The entire goal is to establish a long-term, sustained human presence on the moon. Think of it as our training ground. It's a natural laboratory, and it's the essential stepping stone for humanity's first crewed missions to Mars.
So how in the world do you even begin to plan the science for something this massive? I mean, you can't just show up and start digging around. You need a detailed, a prioritized, and most importantly, a community-approved plan. You need a scientific to-do list for humanity's return. And here it is. This is the playbook, the Artemis III Science Definition Team Report. This is the foundational document that lays out every single scientific priority for the mission. It details what we're going to do, why it's so important, and exactly how we're going to achieve it. It's the result of a huge effort to give this historic mission a crystal clear scientific focus.
So, who wrote this playbook?
Well, NASA assembled a dream team of experts they called the Science Definition Team, or the SDT. They pulled together leading scientists and engineers from NASA centers, from the US Geological Survey, and from universities all over, really to represent the entire scientific community. And NASA gave this team a very specific three-part mission. First, they said, define the core science objectives, make them compelling, but also make sure they're actually doable. Second, figure out what the astronauts physically need to do on the surface to meet those objectives. And third, wrap it all up and deliver that final prioritized report we just saw. Now, this is really important. The Science Definition Team didn't just create this plan in a vacuum. The report was actually built on a foundation of hundreds of white papers that were submitted by scientists from all over the world. This means the priorities we're about to look at represent a true global consensus on what's most important to learn when we go back to the moon. So, what did this global community decide was most important? Well, the entire science plan is built on 7 core objectives. You can think of these as the scientific pillars that are going to support every single activity the astronauts will perform on the lunar surface. Let's just walk through them real quick. They range from these big, broad ideas like understanding planetary processes, how the moon formed and evolved, to a super specific goal, understanding lunar volatiles. That's the hunt for water and other trapped gases. The plan also includes interpreting the moon's impact history, which tells us a ton about Earth's early violent past, and even using the moon as this incredible, stable platform for astronomy. And of course, it covers conducting new experiments and, critically, learning how to keep our astronauts safe on these long missions.
Okay, so those are some pretty ambitious, high-level goals, right? But how do you actually turn a big concept like understand planetary processes into a task an astronaut can do with the tool in their hand? Well, that's where this plan gets incredibly detailed and, honestly, pretty brilliant.
It's all done with something called a traceability matrix, and this is key to the whole plan. It connects the big ideas to specific astronaut tasks. So, for example, it starts with a high-level objective, like understand lunar volatiles. It then traces that down to a more specific science goal, like figure out what the ice is made of. And that goal then gets translated into a concrete, on-the-ground investigation for the astronauts. Drill a core sample in a permanently shadowed region. It creates this direct, logical line from the big why all the way down to the what. And as NASA's chief exploration scientist Jake Bleacher puts it, these volatiles are so much more than just a resource. They're like a frozen archive. They hold a story about how water was delivered to the inner solar system, and by studying them, we can learn about the history of our own planet, Earth. Now, to read that story, the astronauts are going to become expert geological field workers. They'll be trained to collect a whole suite of different samples, because different rocks and soils can answer different questions. They'll take deep core samples with a drill, they'll use a rake to gather up all the small fragments,
They'll grab a quick contingency sample as soon as they land, and they'll carefully select and seal other interesting rocks and soil.
But the real prize, the most critical of these, is the sealed core sample. Now, this isn't just digging up some dirt. It involves drilling deep beneath the surface to pull up this pristine column of lunar soil, or regolith. The sample is then sealed tight and kept cryogenically frozen the entire way back to Earth. And why all the trouble? It's to preserve those precious, delicate volatiles, the trapped gases and the water ice, in their original, untouched state.
Honestly, the best way to think about one of these core samples is as a geological time capsule. The deeper you drill, the further back in time you go. Every single distinct layer you see in that core is like a snapshot from a different era, preserving a 4.5 billion-year-old record of bombardment from asteroids, particles blasted from the sun. It's the whole evolving story of our solar system right there in a tube.
And where do you find the best time capsules? Well, you go to the coldest places on the moon. These permanently shadowed regions right near the lunar poles have basically acted like cosmic deep freezes for billions of years. They are the absolute prime targets for drilling, precisely because they've trapped and preserved these volatile records that have been completely erased everywhere else on the moon.
So all this amazing science isn't just about looking backward in time. Every single sample, every experiment, it's also designed to feed forward, to enable the next phase of human exploration. It's about building the future.
This brings us to a concept that is absolutely central to the whole Artemis program: in situ resource utilization, or ISRU. It's a bit of a technical term, but it stands for a simple, revolutionary idea: living off the land. It just means learning how to find, extract, and use local materials to support our missions. And the science of Artemis III is what's going to make ISRU a reality. Finding that water ice is a total game changer. You can purify it for drinking water, you can crack it into oxygen for breathing, and, this is the big one, you can combine that hydrogen and oxygen to create the most powerful chemical rocket propellant we have. This is how you finally drastically reduce your dependence on Earth for future missions. And by proving we can actually use these resources, the science of Artemis III directly lays the groundwork for the next logical step: the Artemis Base Camp. We're talking about a permanent human outpost on the moon, a place where crews can stay for a month or two at a time, conducting even more advanced science and testing the systems we're going to need for Mars.
And that's really where this is all heading. Every experiment, every core sample, every single bootprint on the moon is part of the larger Moon to Mars strategy. It's all about learning how to live and work on another world that's just 3 days away before we commit to that perilous, months-long journey to the red planet.
You know, the rocks brought back by the Apollo astronauts completely rewrote our understanding of how planets form. Now, armed with brand new tools, targeting brand new locations, and driven by a new generation of explorers, we are about to open a chapter of solar system history that has been frozen shut for eons. So the big question is, what secrets, preserved in that ice for billions of years, will we finally be able to read?